Welcome to this video. Today I'm going to show you how to perform transient simulation with acceleration of impeller for centrifugal pump. So in previous video tutorial we have prepared the steady state case of OpenFOAM simulation and we perform this simulation, and today we change those case and I will show you main difference between steady state and transient simulation case. So let's look the results of simulation. It will be acceleration of rotation impeller and changing of fields with time. Here we have the time dependent boundary conditions. It means we have the time dependent rotation speed and time dependent flow rate. So let's close the video, and in transient case we will have to download the some example of OpenFOAM case I prepared, and you can download it on GitHub. So I will show you how you can download it. Let's go to my repository. Let's go here, repositories. Here you can find FreeCAD OpenFOAM Velocity, and here you can find the transient case. So let's download this zip archive. Wait some time and let's paste it in our working directory and extract it here. After that we have to use this transient case and paste it here. Let's delete this FreeCAD OpenFOAM Velocity GitHub file and let's paste it to this root of our project. Let's delete this transient case, and here we have some directories of OpenFOAM case. Here we have the initial boundary condition. Here we have some settings of our simulation, and here also we have some settings of our solver, schemes, and another setup of delta t. It is a time step and another settings. So here let's let's create the form.foam file. We will be using it for open the project in Paraview software. Paraview software you can download in Paraview. In Paraview you can Google it. Site. Okay, Paraview, and you can see this site, paraview.org. You can download here in Paraview software. You can choose it for Windows, for example, or you can download the Paraview for Linux also. You can choose this system for Linux. Okay, so let's go to folder the directory 0. Here I will show you what's difference with steady state case. Here we have to open the velocity file, and in velocity file you can find some changes. Here we have the difference with steady state case. The steady state case of OpenFOAM simulation of the pump, centrifugal pump, you can find on my channel. It is a previous video tutorial. So let's look to this file. The first changes we have for flow rate inlet velocity. For volumetric flow rate, now we have not fixed value, we have the time dependent boundary condition. It means in table we have the first column is a time of simulation, and the second column we have the value of volumetric flow rate here. It means that from 0.0 to 0.02 second we have the linear ramp, the linear dependencies between volumetric flow rate. The volumetric flow rate increases from this value to this value with 0.02 seconds, and for end of simulation we have the constant value of volumetric flow rate. This is this value. Okay, so, and one else changes we have here, it's we have to use the moving wall velocity for our wall of impeller. In steady state case we use for wall impeller no slip, it also like for a stator region. But for dynamic meshes, when we have rotation or another some changes with mesh, we have to use this moving wall velocity boundary condition here. So let's close this velocity, and for another files we have similar setups like in our steady state case here also. So let's go to constant directory, and here we have changes with multiple reference frame properties. We change to dynamic mesh dict. The dynamic mesh dict, it means that we use not a stator mesh, we perform some manipulation with mesh. For our case we have rotation motion, and here you can see what libraries we use for this dynamic mesh solver FreeCAD this library. And here we use the rotor region, we called it in set utility of OpenFOAM in previous video tutorial, and here we set rotation motion, a type of our mesh, dynamic mesh. So here we have this position of rotation axis in coordinate system, and here we have to choose axis of rotation. We have the X direction. So for omega we want to set some acceleration for our rotor impeller, and we use also the table with these values. It means also first column will be a time, and the second column will be a rotation speed in radian per second. For 0 time we have 0 rotation speed, and for 0.02 time second we have the full rotation speed, and it will be increased linearly. And for next time we have a constant value of rotation speed. It's a similar like in with boundary condition for volumetric flow rate inlet on inlet. So this is a main difference with steady state case. And let's close this dynamic mesh dict, and after that let's go to system. Here we have some changes with control dict. Here we use the pimpleFoam solver, and for steady state simulation we use simpleFoam. solver. And here we have a start time 0 and time 10 seconds. In steady state case we use iterations. Here we use the physical time, and we have here the time step is a delta t per in seconds. And for this value, it's a not constant value delta t, because we use the maximum current criteria. I set 100 maximum current number and activate these changes with delta t. It means the first iteration will be this value. After that we OpenFOAM calculate current number and change this delta t for this criteria. Okay, so after that we have the functions. We use also these functions in steady state case. So let's close control dict and let's go to FreeCAD schemes. In FreeCAD schemes we also have difference. With steady state case, the main difference will be that for delta t scheme we have the error. It means that our flow field depends from time. In steady state case we have here steady state, meaning another settings we have not very much difference between steady state case. And I will close this FreeCAD schemes file. After that I will open the FreeCAD solution. In FreeCAD solution we have the solver settings, and here we have the some additional of a solver settings with for example, for pressure we have the pressure final, and it means that for our transient simulation in our one time step we will be performing a steady state simulation with several iterations, and the first several iteration will have these settings for solver, and the last one will be the p-final iteration. And after that, after p-final's iteration, the solver change the time step of transient simulation, and flow field will be changed. So this final we have for all our fields. We can to write it in this one row and merge them, and we use the settings for k omega like as in our u here variable. These settings of smooth solver we have here also, because this is a link between them, and we have some additional settings with tolerance, relative tolerance. Okay, after that I will show you what difference with here. We have the pimple. In steady state we have a simple algorithm, but I have the non-orthogonal characters too, because I have not very good mesh. It's a tetrahedral mesh with high non-orthogonality quality. If you perform the check mesh, you can see that our non-orthogonality higher than 55, 50, 77, how I remember. And here we have the number of maximum number of iteration per one time step. It's something like a steady state solution in one time step simulation. And here if our residuals control not converged for these tolerances for U and P fields, the solver will perform only 50 iterations per one time step. But if we have got this convergence with our fields for residuals, the solver go out from iterations and change the time step. So here we have the relaxation factor for transient simulation. For pressure we have 0.3. It will increase the stability of simulation, and final it will perform a correct correction for our field per time. It means if you decrease this, you cannot use your changes with time, because your field will be changed not correctly with time per time. It means that we have to use p final equal 1 for transient simulation. Okay, so PV solution is set up, so let's close this, and these all changes which we have performed with steady state case solution. And after that, let's try to run this simulation. Let's go to this directory I here now, and let's make a decomposition our case, decompose par command, because we want to run simulation in parallel mode. If you have less number of cores than 12, you can change the number of cores which you want to use in decompose predict here. If you go here, I have here number of subdomains. It means that I want to use 12 cores of my CPU, and if you have 8 cores, you can set here 8, and here you have to use multiply all this coefficient in different direction, in X direction, Y direction, and Z direction. It's a split of mesh, and multiply all them. You have to get your number of subdomains. Means 2 multiplied by 2, it will be 4, and 4 multiplied by 2, it will be 8. You have to use this coefficient here, or you also can set here something like this, and you will also get a correct parallel simulation because you have the multiplied coefficients here also 8. So let's set here the default settings which I have for my CPU, and let's run a simulation in parallel mode. I open it on full screen, and I will paste here I run minus np number of cores solver which we want to use pimpleFoam, and minus parallel. This is a command which you can use for parallel simulation running. So press enter, and simulation is run. Okay, and here you can see what current number we have, what time have, delta t, the time step, and the values of residuals. How can you see? We have some very small value of our residuals. It means that we have the high accuracy of simulation here and stable simulation. And the last iteration is 13, but for our outer control for pimple algorithm, the maximum number of this iteration will be 50 in control dict file. And how can you see, this is the last iteration, and solver change the time step. Here you can see what time simulation we have here, and run next steady state simulation for this time step. Okay, let's wait some time, and here you can find some results of your simulation for different time steps. And let's open the Paraview. You can open Paraview using the exe file. I just to add this Paraview exe file to my environment. Okay, and I open a project of transient case, open the OpenFOAM file, and here we have to click apply, but here, how can you see, we don't have the sum results, we only have the mesh. If you want to use these results for parallel mode, you have to change the reconstructed case to decomposed case. Let's change it, and how can you see, we have got these time steps, and we have here the fields. So let's use, for example, U field, and let's go to another, and you can see that our field is changed. If you will go to 33, for example, and click here, change your ranges of velocity. I will set here the maximum 30, and here I will set 35 maybe. Here I will set 0, rescale it, and I see velocity field with these ranges. And if I will go to our first time step, I have very small value of velocity. It means that here we have almost 0 velocity. And if we will change our time step, how can you see the rotor perform some changes in position, and velocity increase with time. And if you will run, just here click it, you can see that our rotor perform acceleration of rotation. And if we will perform the reload files, we can to download last results of our simulation. And let's run animation, and how can you see, we have some changes with rotation and some changes with velocity. Of course, you can, for example, perform some changes for better visualization. Let's set the background to this white. Let's change the value of velocity here, the color of these values of velocity. Let's go to these settings here, and let's change the color for our bar here. Click OK, and how can you see, now we have the black color for our values of velocity. Okay, and also we can, for example, make a split of this geometry. Change it and perform a split. And how looks internal fluid flow of our pump. So let's hide the panel, and also you can go this and change, for example, for velocity, set velocity range 0.35, rescale it, and let's just run, and let's see how increase rotation speed and change velocity field in our simulation. Let's reload the last results and run it again. So now it works. Let's check the values of moment. It looks a correct moment because we have something similar for steady state case. And let's stop our simulation. You can use the Control C. On your keyboard, press Control with C K, and you will stop simulation. Okay, so let's go here. Here you can find all your steps of your simulation. So here we have the results. So thank you for watching. Subscribe to the channel. Goodbye.